Hi, my name is Hee-Seung from Aalto University and Yonsei University. This talk introduces a new way of decoding user behavior with user simulation models. For user simulation researchers, this will be a more efficient way to fit and evaluate user models with empirical data. What can user behavior tell us about the user? Let's say here's a user typing a text with their smartphone. We observe how many words they are typing per minute and how accurate it is. We can think of several factors of a user that will affect typing behavior. For example, some users may have better motor capability on fingers, or some users just prefer to type fast, while others focus on minimizing typos. This work explores how to identify these unobservable factors from observed behavior. We show that amortized inference can be a novel, efficient, and robust way for achieving this goal. User simulation models can reveal how the factors of a user affect their behavior. These are programs that reproduce the user's sequence of actions to perform a task. Each model has unique parameters that can describe specific users. For example, one can adjust the model's parameters to simulate users with different levels of motor noise. Recent advances in machine learning have opened new opportunities to address the high dimensionality of human behavior. Therefore, there have been remarkable works in reproducing user behavior across various interactive tasks. The simulation of the user behavior from model parameters can be referred as forward modeling. Meanwhile, each opposite problem can answer our first question about characterization of users from the observation. It is called inverse modeling, and this can be regarded as model fitting to identify the parameters from the given data. Inverse modeling has several applications in human-computer interaction. First, by inferring the model parameters from behavior, we can better characterize the user. Second, the model fitted to individual users will show enhanced prediction for that individual's specific behavior. Also, the inferred parameters can serve as a basis for personalizing user interfaces. Finally, inverse modeling is a crucial step in the development of new models, allowing us for verifying the model against empirical data. To make these applications more robust, it's important to identify the uncertainty of the inference results. Therefore, the goal of the inverse modeling has usually been to estimate the entire distribution of the model parameters. However, the inverse modeling problem has been challenging due to its computational intensity from simulations. Conventional methods estimate parameter distributions by comparing discrepancies between observation from actual user and simulated behavior. Consider space that can express all possible behavioral data from users, and suppose we have observation data from a user. And the simulation model can reproduce user behavior from different model parameters. Model parameters that simulate behavior closer to observations will have a higher probability to represent that user. The main problem with the previous method is that simulation is time-consuming and it requires a complete estimation process to infer for every new observation. Therefore, inference with simulation models often took several hours or even days for single observations. In this work, we introduced the recent amortized inference technique to solve this problem. Amortized inference builds a neural proxy model called a density estimator to reduce the cost of inference. With this proxy model, we can instantly perform inference on each user, taking less than a second per inference. This will help to understand the concept of amortization. Without amortization, the cost of inference can be high for every new observation. But with a density estimator, inference costs are amortized by upfront model training. And then this amortized cost is reusable for every new inference, making it easy to scale up. In our inverse modeling process, we train a density estimator using only the simulated data from the user model. The trained density estimator is then deployed to infer actual user data at a significantly reduced computational cost. The main technical challenge of amortized inference is to identify complex distributions of model parameters from observation data using a neural network model. Estimating this complex distribution has been a difficult problem in machine learning. But thanks to recent deep learning technique called normalizing flows, we now can tackle this challenge. Normalizing flows is a technique to transform a simple distribution into a more complex one that approximates the target distribution we want to identify. It works by using a series of invertible transformations based on a neural network, which is called flow steps, to gradually map the latent parameters from a simple distribution to the target parameters. Therefore, when we have observation data, we begin by sampling latent parameters from a normal distribution. Then, we use a trained density estimator to transform these into model parameters, allowing us to identify the distribution of the inferred parameters. We conducted 3 case studies that applied amortized inference to 3 different user simulation models and feed them to empirical user datasets. First, we feed a model of menu search behavior based on user data of their simple performance. Then, we considered more complex data types, feeding a model of point-and-click behavior using time series observation data like mouse trajectory. Finally, we showed that a larger scale of inverse modeling is possible by feeding a touchscreen typing model to an empirical dataset of over 1,000 users. Our research demonstrates that amortized inference can speed up the model feeding process to less than a second across all cases. Previous publications have reported that feeding each simulation model took hours or days with conventional inverse modeling methods. However, with amortized inference, feeding time is greatly reduced as it only requires a single pass of data through the density estimator. Second, the model fitted with amortized inference showed better prediction accuracy than the previous approach in all cases. We compared the accuracy of the fitted models in replicating actual user behavior. In a touchscreen typing case, we measured discrepancy between simulated and actual behavior across 4 different typing metrics. A single model fitted to the entire dataset with amortized inference showed better prediction accuracy than the previous method. Additionally, feeding a model to each individual user with amortized inference allowed for personalized behavior prediction with enhanced accuracy. Finally, amortized inference made it possible to identify parameters for over 1,000 individuals with a short time. This offered researchers a new way to analyze large-scale behavior data and gain deeper insights about users. For example, we can investigate how parameter values inferred for each individual are distributed in the population. In our study, we found a significant correlation between demographic factors and the parameter values of users' finger motor capability, showing that younger and female users have better motor skills of the finger. In summary, the main takeaway of this work is that amortized inference offers a faster and more robust way to decode user behavior with simulation models. We showed that it speeds up the inference process to less than a second, and its high efficiency enables individual level prediction, and large-scale data analysis. That was the end of the presentation. Thank you for listening.